So I'm Krister, and I'm going to talk a bit about undefined behavior in C++ and what the compiler actually used that for. So I guess most of you have seen something like this that always come up every time in discussions on the net, that when the compiler encounters, well, some construct, so it can do whatever, and including make demons fly out of your nose. And this is not really helpful. Um, it mostly confuses the issue. People think that undefined behavior is something scary and something compiler developers have invented just to screw up your code. But there are actually real reasons why we must have this for C and C++. So the problem comes a bit that, well, we used to like to say that C and C++ should be as close to the metal as possible. It should not be possible to have a language under it. So we want here to so if you have code like this, we think of it that we put things on the stack and so on. So here we allocate 3 integers on the stack and add them together. And if we naively just compile this, we get this. And none of you would like this, I guess. Would like something more like this, what you get after optimization. But in order for the compiler to be able to optimize, we must be a little bit more abstract than this bit and byte thing. So the standard says what each construct mean, and the compiler can do whatever it wants to do as long as it gives the same end result according to the rules. So let's say we have a pointer here. This pointer points to some memory. So it can, when we write 0 to it, we don't really know which memory we change. But the compiler still optimizes this. So why is it allowed to do this? Because, well, P could have changed something in A. Well, the reason here is that the standard says that when you create a pointer, you can only do it in certain ways. So you can get the pointer when you create an object with new and that kind of thing. You can get the pointer by using the AND operator. You can get a new pointer from an existing pointer by doing pointer arithmetic, but there are rules that you must still be within your object and not going outside of it. So if you look here, there is no way that P can point on A because, well, it has not done anything of that. So we come to this that I know which address my stack is on. So if I send this address into Foo, then Foo will give me the wrong result because I expect it here to give me 5 instead because I give it the first address on the stack, so it should overwrite the first element. And that is where the undefined behavior come in. So it's not allowed for a program to do this. So if the program does this, the behavior is undefined, and this means that the result can be whatever. So that means that the compiler can just assume that the undefined behavior does not happen. And as you see here that this is needed in order to optimize when we have a random pointer involved in the code. So in general, in order to optimize where there are pointers involved, we need this kind of reasoning because otherwise we would need to write back everything to memory and read it back after every pointer access. So this use of undefined behavior is a fundamental part of C++. What we can discuss, on the other hand, is exactly what construct should be undefined behavior. And we will look at some later in this talk that maybe should not be. So we continue a little bit about pointers. As I said, there are just a few rules how you can get a new pointer or modify pointers. And the compiler spent quite a lot of effort keeping track of all the pointers and see what they can point to so it can do other optimizations. So the compiler can also use this data when it optimize comparisons. So let's say we have this if p is equal to q. So if p and q cannot point on the same memory, then they are not the same. Note that this is a little bit more abstract than thinking of pointers as the bit values, because this says that it have not been able to calculate compatible pointers, but it may still have the same bit value. So to give an example, what can go wrong? We have a function here where we have two integer arrays, x and y. And we take the address of two elements of them. And as you noted, for p, we are out of bounds. So as GCC lays them out in memory, they will actually point to the same address. But when the compiler does its analysis, it sees that p and q, they are different arrays. So of course they are different. So it can optimize this to if true. So when I run this, it prints this, that those two pointers are different, even though they have the same value. This is probably nothing that will bite you in reality, but it's good to know that a lot of the underlying information is more abstract than what you may think if you have not looked at the standard. Another fun example that circulated a bit on the net a while back was this, where undefined behavior may make a program call a function that you are not calling in your program. So let's look at this. In the top here, we define a function pointer do. This is static, so it is local for this file, and it's automatically initialized to the null pointer. And if you look at in the main function here, we call it. So you could expect it to crash because, well, we call a null pointer. But if you compile this with Clang 6, you will get this. So it calls system with rm.rf. So the question is, what is the compiler doing? And if you go back to the first slide, since this is undefined behavior, the compiler can do exactly what it wants. But it doesn't do this just to be evil. It actually follows out from how the normal reasoning works. So to begin with, calling a function pointer is sort of common in C++, but you have virtual functions and so on. So the compilers want to try to see what it jumps to, because often there is only one choice. And if the compiler can figure out that, it can then inline and do all the normal optimizations. So when it sees a function pointer, it starts to do an analysis. It sees that what's said is a local. The function pointer here is local for this file, so it knows that all possible values are set in this file. So it starts as null, and they go through the file and see what else can write to it. And they see that, oh, they never called. It may set it to erase all. Okay, so we have two possible values. And now we go next step and say, okay, we have two values. Null is one possible value, but that would be absurd because that's the undefined behavior. So we can remove that from our Oh, so we only have one possible value now. So let's inline it. And you get this result. So for example, let's say we had two functions that set do in this one. Then we would not have a problem because we will see here all the two possible versions, nothing to do. And then you will get your crash as expected. But this kind of harmless, that it is conservative and actually adds more possible choices, can cause strange results. So, so the question is if doesn't say that standard is lacking in some way, and some people would argue yes. But this comes back to this with undefined behavior. What construct we say is undefined behavior and what we can use with it. So let's say we should say that it's invalid but implementation specified. We could still get sort of the same result because we are doing rather harmless steps one at a time. So it's very hard to specify rules that cannot cause problems. You more or less need to do something like Rust that only permits certain things at compile time, and then but it is possible to make it more safe. And this also comes back to well, quality of implementation, how much advantage the compiler takes of this. For example, GCC is try to be careful to actually preserve all null accesses, so you get a crash, and it does normally not do this optimization. But it has other problems that we will come to soon. So as I said, with null pointer accesses, that GCC tries to keep them. But that doesn't mean that it do not optimize away null checks and so on, because it's quite often you get this kind of thing after inlining and so on, that you're using some element, you're sending it to another function that checks that the parameters are okay, and then does something. And after inlining, you get something here. So the compiler may assume that P is different from 0 here, different from null here. And if you want to look at it in an intuitive way, you can say that if P is null, then it will have crashed here. So therefore, we can optimize away this anyway. So that seems like a nice and safe thing to do. But there were quite a lot written about this 10 years ago, when this caused arbitrary access to the Linux kernel. So it was a driver that had code looking like this. I think it was a network driver. So it was a mistake. It wasn't meant to crash when it got null. It was actually meant to check and return the error. But they switched the order of the statements by mistake. And in general, that's not a big problem. You get a kernel panic instead. But an attacker could use mmap to map some memory on address 0. And by crafting packets on in a correct way, could change arbitrary memory in the kernel and get root access from that. So even this kind of harmless optimization that, yeah, we know that it would have crashed, so we optimize away, does not always be right in all certain cases. So for example, the Linux kernel disabled this optimization to to try to be more safe. Okay, so we go over a bit to integers. So signed integers cannot wrap. So that is if you have an integer x that is the maximum value and add 1 to it. That is undefined behavior. And the nice thing with this is that integers work sort of as with mathematics. So if you have x plus 1 is less than y plus 1, then we can subtract 1 from both sides of the relation, and it's true that x is less than y. So that is nice when you optimize. So there are a couple of different rules for optimization we can do. All of them are similar. And this may not seem that exciting, but again, it's happened quite a lot after template instantiation, inlining, and so on and so on. And it's possible to write programs so this doesn't matter at all. Some programs makes it matter a lot. So that is why compilers do this. But this is one of the rules that many people now try to get rid of, and there have been discussions in the C++ committee to actually make wrapping defined, even that it doesn't seem to happen. But it also makes it easier for the compiler. So it's often good for a compiler to track possible values to make optimizations. So if you have some code like this, we see from the first one that x can be whatever. After the if statement, if we goes into it, then we know that it's between 1 and int max. And when we add 5, since it cannot wrap, we know that it's between 6 and int max. So here we know that y is non-negative, and we can optimize this to normal bit shift, which will not be possible otherwise. So the thing that we have no wrapping means also that we usually have one range. If we had tracked values in otherwise, we will get lots of sub-ranges. So of the first, it could be either int min to int min plus 5, or the top one, and so on. And it very fast get so complicated it's not worth trying to track them. But here we can usually have rather good knowledge about the values. So we can then optimize away different checks and so on. One other thing that are helped by having wrapping undefined is indexing into arrays. So you look at this. If we allow the wrapping, then it could be the case that P points in the middle of a 4 GB array. So when I plus n overflow, so actually what this program wants to do is write 42 to the top and bottom of this array. If you do not allow wrapping, then we know that all the accesses are consecutive. That makes it possible to do better code. So for example, if we start here, if we had wrapping, then we need to truncate each iterate of the loop in case I plus n overflowed. And if we, as now, do not allow wrapping, then we get rid of that. So you get one instruction less in the loop, and that often matters in this kind of accesses because it will be on the critical line. So you will have longer dependency chains that may cause stalls. And also if you want to vectorize and so on, we need that accesses to be consecutive. So we will also have problems with that kind of thing. For people who do not like this undefined of wrapping integers, they say that, okay, use a 64-bit type for your indexing instead and you're safe. So that is a choice. In GCC and Clang, you can disable the undefinedness of wrapping with a flag, fwrap-v. One other thing that you often see discussions about where people hate GCC is the aggressive loop optimizations. So let's say we have a loop like this. It's a little bit unclear to the compiler what to do here. It's a good candidate for vectorization, but that depends on the value of n. If you have small loops, then there's a lot of overhead doing vectorization, so that is bad. If it's small, then maybe you should do some partial unrolling and so on, and there are different options. But if the compiler sees that A is an float array with 4 elements, it can see that it will be a buffer overflow if n is bigger than 4. And that is undefined behavior, so it can optimize this as if n is equal to 4 or smaller. So in this case, it will probably not vectorize this. And this, of course, can give interesting results if you have bugs in your program. So here's one example from Stack Overflow where someone complained that the compiler must be buggy. So this is a function that tries to see if the value v exists in the table, and it has this for loop that iterates it, and if it finds it, it returns true, otherwise it returns false. But here is a small error. It should of course be just less than. So the compiler sees that the table only has 4 elements. And here we use I, so it knows that I must be in the range 0 to 3. So this is unreachable, because this only happens after I is 4. That also means that this is always true. So by doing that, it can change the compare and branch to just a conditional branch that then helps other optimization maybe. If you look at in this loop, we don't have any side effect at all. We know that it must return, and it's only one return statement. So we can optimize this too. One confusion about undefined behavior is also that if you change something a little bit, it can be completely different. So if you look at slightly different, slightly more complicated function here. So here we print the value each iteration. Okay, change font here, but anyway, first step is the same. So we see that we can remove this and make the loop infinite. And we now have side effects in this. We cannot just return true. So if you had this function, it would be reasonable for compiler to do an infinite loop here that just prints out byte for byte after array until it crashes. The compiler could also, depending on other circumstances, see that, okay, this only iterates 4 times, so we can unroll the loop. In this case, we get a program that works correct sometimes, depending on if you have your value in the beginning of the array or not. Anyway, it will always return true, but, well, if it was in the beginning, that's what it intended, otherwise it does not. So this is why you get this kind of Heisen bugs, where you get really not deterministic behavior that you want to do some debugging, you add a print, then suddenly something completely different happens. The question was at what optimization level this happen. I think it's the aggressive loop optimization is O2. And so if you are scared for this particular case, that there are also flag to disable that one. If you actually, if you are running the spec benchmarks, then one of those applications have this bug. So you need to use the flag there. Okay, so that was mostly what I wanted to say today. So, but it's customary to say a few words about how to try to avoid these problems. So if you're using GCC or Clang, there are 3 things that I think are good to know. One is to use the warning levels. The warnings usually tell you about many of the potential problems. We have the sanitizers that instruments the code, so try to detect, I think, all of the problems I have told you about today. It doesn't catch all undefined behavior, but the majority of the cases. And finally, if you add these debug flags, then it enabled additional checking in the libstdc++. So for example, it checks that iterators are within the containers. Some algorithm requires the input to be, for example, sorted. So it checks that the input actually is sorted, and so on. It will cause an assertion if it triggers. And of course, the program may be much slower depending on what you are doing. If you have large array and it needs to check that they are sorted each time, that can be painful. So that's it. So questions?
I have a question. The last bit. You said cause and assertion.
Yep.
What does that mean?
It just
Really super stupid here.
so it just prints out in the code. You have the assertion macro.
Yeah.
So it just what happened here is that it adds assertion macros all over the place essentially. So you will get.
My colleagues always say cause and assertion,
Mhm.
and I internally have translated that to assertion failure. But
Cause yeah,
I think it's a language thing.
assertion failure is probably the right word. Yes.
Yeah, yeah, okay. I wasn't sure if you were using it in the same way that my colleagues use it. So, yeah, thank you. Sorry.
Thank you. Yes.
Two things. First thing is, I think you have some logging in your slide. You should have some brackets. Go back to that.
This one.
Yeah.
Okay.
How the indentation is stored.
Yeah. Yeah. Right. That's true. Yeah.
But I have a question about that RM RF.
Uh, that one.
Does all of this bad things happen just because Q isn't assigned null, which I would expect it? Because I would expect a regular integer assigned.
Right. This is just a pointer issue. So it is that it is null. Hello, well, the null pointer. That is the problem here. Yes, because this is a function pointer. So so it doesn't point to anything. So that is the issue here. could behave in the same way. I would guess, since I'm not that used to Clang and LLVM, but I would guess that this optimization is used for virtual functions. So it doesn't really track other pointers than functions. But it definitely could happen, and it's sort of a reasonable optimization to do this kind of thing for other pointers too.
But you encountered this just on Clang, not GCC and some specific version of Clang?
I think all recent versions of Clang. When I played with this a while back, I wrote a blog post about it and so on, and Clang 6 did it. GCC doesn't do this. I guess you can, well, you may be able to do it with GCC if you enable some special flags. But as I mentioned before also, that GCC tries to preserve null pointer crashes. So I'm not sure how that interacts with this one. But I could guess that function pointers are different from normal pointers, so it may try less to preserve it there, because there are different parts of the internal infrastructure of the compiler that track those different. Okay, so no more questions. Thank you.